I had some travel delays and flew in early morning today and Ubered in from San Antonio. It was a crazy, crazy day. So just forgive me if I'm like, take a nap in the middle of this. I hope not to, but just FYI. So anyways, I'm Alejandro Barreto. I work at NI. NI is one of the original tech companies here in Austin, along with Dell and IBM. We've been around for a long time. We just got bought out by Emerson, so you'll see both logos down there. I'm a chief software engineer working in the CTO office, and what I do is AI all day, every day. And so I've been working with AI for the last, I would say, like 2 years before ChatGPT, along with my awesome colleague, Andrew Dove. Together we do all the AI. We set strategy, we do prototypes, we code. It's like a lot of everything and things like this. So I'm very excited to talk to you about how we're bringing AI to our customers. I do both external stuff and internal stuff. So in the internal side, for instance, we have every engineer has access to GitHub Copilot and many other AI tools. And then I spend a lot of my time now this year looking at how we're going to put AI in the stuff that we sell. And so first we're going to start off with who are we? What is NI? And what is this idea of intelligent test, which is how we're going to bring AI to our customers. Then we're going to show some demos. We have to show some real things that work. Then we're going to talk about an alternative to RAG. So you've probably heard RAG at this conference or elsewhere, retrieval augmented generation. We have perhaps a different way of doing that we can share, and we'll get into some more technical details on that. And then we're going to talk about some takeaways about what we've learned about putting AI into our products. So let's get started. Who here is a software engineer? So most people. And you write tests for your software, right? Hopefully, it's hard sometimes, but it's something that software people do. We write tests. Well, that's also true for the real world. In the real world, whether you're building, a 6G wireless network, 5G, all the components that go into wireless networks, medical devices, if you're building self-driving cars, or the latest fighter jet or spaceship, you're going to want to test every component that you have in there. So let's dive into a single one of them, aerospace. So obviously, I just flew in from New York City today, and everybody's flown on a plane, right? I would imagine so. And hopefully that plane was tested, so you felt safe being on it. We sort of don't even think about it. We just get on the plane, this magic, super heavy metal thing flying through the air, with all this fuel and all our lives in it, and we trust it. And the reason we trust it is not just for the pilots are highly trained, but it's also for all the testing that went into every single device that makes up the plane. So here you can see some examples of what you would do to a plane. You would put it in a wind tunnel, you do acoustic tests, so that one's really interesting because they put out thousands of microphones over a runway, and then they fly the plane over it, and they try to figure out how loud it is at different altitudes, at different environmental conditions. You do flight test control systems. So this is also for SpaceX, a lot of the launch operations are run using our software and hardware. It's super cool. And so these are the types of things that you would want to do to test your products. And so that's what we do at NI. We allow you to test your real cyber-physical systems, the real things that you put out, the cars you drive, the phones you use. That's what we allow you to do, the chips in every single one of our laptops and phones. And the reason you would want to do this is to ensure that you have increased yield in manufacturing, that you have a product that has high quality, that you can build it at low cost because you don't have all the returns, that it meets the safety. Again, we just talked about a plane. Plane safety is very important. You have to test it. And then also we allow you to have the tools to understand how well your device is working so you can feed that information back to R&D and build a better product in the second version. So the way that it's traditionally done, hardware testing, is you're probably familiar with a lab that might look something like this. Maybe you saw this in college, maybe you're a hardware company and you have people that work in rooms that have lots and lots of boxes with knobs and wires everywhere. And so this is the way that traditionally testing has been done for hardware. But this has a bunch of challenges. As you can imagine with all these different boxes, it's hard you have different interfaces for each one, different APIs for the different software, different ways to talk to them, different ways to connect them to each other. They might not even be compatible. It's really hard to reproduce this setup. It's also very expensive. And you have all these different screens. And and you can't customize it very well because you get what's in the box. Whatever's in the box, whatever's in a DMM and the scope, that's what you get. And so NI turned this around many decades ago, and we have modular instrumentation. And what that means is that every single one of those slots in this PXI chassis, PXI is basically a computer that's been flipped around backwards, facing front, and it's been made more industrial, I suppose. Each one of those modules replaces one of those boxes you saw in the previous picture. And then you have a high-end computer with Xeon processors that allow you to crunch all that data and then also bring it into the cloud. And then you have software, so instead of having little screens that do only what they've been programmed to do, you can write software and test your device however it is that you want. So let's zoom into the software. NI is well known for LabVIEW. LabVIEW is a graphical programming environment where you draw essentially your programs, and you can draw your user interfaces. So if you're looking at SpaceX launch control systems, a lot of their screens are going to be in LabVIEW. It's a very easy programming language. It's meant for non-programmers to be able to control the real world. Then up-leveling it, we have TestStand. And TestStand is bringing in all those test programs into a higher level sequence editor so you can run different tests in manufacturing. So if you think about it like XUnit, if you're a software engineer, NUnit, JUnit, whatever, all those, that test stand is that, but for the factory, for the manufacturing floor. So one of the challenges that we've been seeing is that systems are getting more and more complex. It's actually pretty easy, perhaps, to do an acoustic test. Whoa, where's that? There it is. But now you're getting systems such as a self-driving car that are systems of systems. They have cameras, they have LiDARs, they have every light bulb, all the lights are their own computers. So it's a connected, distributed system that your car is actually very, very complex. It's like a rolling data center. So how do you test that? And how do you test that when people are putting in AI in different conditions? It gets very complicated. And so what we've been seeing in the industry is that the ability to manage this complexity is outpacing the tools and environments that we have. And so this is actually a study done that applied for IT, but we're seeing this applied in every industry, not just IT, but in the real actual manufacturing. Beyond that, we have done a survey. So we surveyed a couple thousand customers and non-customers in manufacturing. And we asked them what their challenges were if they saw this trend actually be true, and they agreed. 57% fear that their production processes are outdated and cannot keep up with new business and technology trends, such as AI, such as cloud. 46% say they're going to lose market share if they don't do something very different in the next 2 years. So what we're here to say is that perhaps AI is one of those things that can help bridge that gap, help narrow that gap. And we believe the test leaders of tomorrow are going to be the ones that embrace AI today. And the way that we bring that in is through what we call intelligent test. So we are putting AI in the actual hardware. So all those modules, all the actual physical hardware is going to have AI in it. You're going to be able to make precision, acquire data in intelligent ways. We're also putting it in the actual apps themselves. We're seeing this a lot industry-wide, right? Microsoft Copilot is user intelligence. It's the ability to improve your workflow and make it more productive. But we also believe that there's an enterprise intelligence as well, which is improving the workflow of an entire team, of an entire organization by giving higher level insights to business leaders through AI, through analytics, that is beyond just, oh yeah, can I make my test program a little faster? Or can you debug this thing? Help me debug this thing. So that's what intelligent test is. It's hardware, software, and then the entire enterprise intelligence. And we have a way to build this thing through our AI best practices. So obviously, we believe that we want to put the human in control. We want to have experts lead the process. So no matter how powerful the AI gets, the human is going to be in control and being able to use their expertise that they went to school, that they know the plane better than any AI does right now. And so we want to put them in charge. And we want them to be able to trust it. And then on top of that, we are obviously making it very, what we call industry ready. Some of the customers we sell to will never put any of their data in the cloud. And so we say safety, security, where the data goes, all that is something that we care about a lot, and we talk a lot about it. So let's dive into one of the use cases that we have here, the spec to test workflow that we demoed a year and a half ago at our customer conference, global customer conference. And what we showed is that you can take a whole bunch of your spec documents, your data sheets on this. This was an op-amp, so an amplifier. It's a little chip that makes your signals bigger, amplifies them. You can take your data sheets on that and some descriptions of your tests and feed it into Nigel, which is what we call our intelligent chatbot. And it will bounce, it will co-design this with you. I'll ask you questions. It will give you wiring diagrams. It will actually give you everything you need to run a test on it. So the VIs and the test stand sequences. It will give you everything. How to wire the thing, what hardware you need, the program itself, the sequence. And then beyond that, it can also then run the sequence for you, or run the test programs, and then analyze the results and help you figure out how you're going to improve your test program if there's a bug, or how you're going to improve the actual device. So we call this workflow spec to test, and we've been working on it for now many years. So these are old screenshots. And we believe that there's actually a lot of use cases for AI, even beyond chatbots. So this is just an eye chart. I'm just going to highlight a couple of these. Optical defect detection. Can we, using a camera, detect that a device was mis-soldered? You know, take a picture of the thing automatically and look, oh yeah, this is where these soldering points are not right. That's just one example. Predictive or just-in-time maintenance. If we have the tests for the device, can we run them all the time? Can we figure out if we need to send a technician to go take a look at a piece of equipment? And then AI-based root cause analysis, which we're going to deep dive a little bit. This is not an exhaustive list. This is an old slide. We have many more things that we've been working on, but this is, I just want to highlight some of the ways that you can use traditional ML to improve the workflow of users beyond just a chatbot. And so let's take a look at how we've put together root cause analysis and a chatbot together in this video. Well, let's explore this idea together. So I've loaded up the data that Shruti ran on stage. It is the small signal gain for our amplifier. We're characterizing the performance and the test limit for this amplifier. And I'm wondering, can we do better? I see this faint line here. I'm just going to draw this arrow here, say, hey, Nigel, why is this so low? And just a heads up, we're going to speed up this video in the interest of time, but everything you're seeing here is real. Okay, great. Looks like the AI replied, and it's telling me that this faint curve could be because of a variety of factors, such as variability in the DUT performance, or measurement errors, perhaps at the test station, and that this curve is actually potentially bringing down my limits. And it's telling me that to further investigate, it might be useful to examine the distribution of small signal gain values more closely. So let's do that. Okay, well, the AI replied with a distribution of small signal gain around that frequency, 8.5 gigahertz. And I see here this distribution is bimodal. So I'm just wondering, I'm just going to circle these samples here and ask Nigel, examine why these samples exist. Awesome. Well, it looks like Nigel created a distribution here of the small signal gain around the frequency that I had placed my arrow. And it's giving me some statistics.
Is the video updating?
These observations here. So it's saying here that all of the samples come from the same test station, TS002, which might suggest a station-specific issue. And that, furthermore, there are 25 different DUTs in these samples, and that might indicate that the issue is not isolated to a specific device, but could actually really be the test setup or the conditions at the station. And it's suggesting that we should examine this station. Let's ask the AI to plot the gains for all test stations for all frequencies. Great.
So it looks like the AI created a chart here plotting the gains across all test stations at all frequencies. And we can see here that test station 2 is definitely lower for all the measurements. So something must be off about this test station. Perhaps it's a loose cable. We're going to have to investigate that. But for now, let's just ask Nigel to redo the first chart with the test limits, but without TS002, and show me the improvements in the performance and limits in a table, if any. Awesome. So it looks like excluding the bad test station led to a 1 dB increase in the amplifier's gain. The typical performance now rounds up to 33 dB, and that's a better number that we can include in the data sheet. This more precise characterization of the gain is a big deal in RF applications where every decibel counts. So what we just saw was that the AI analyzed our measurement data, crunched some numbers, and helped us diagnose an issue at the test station, all of which led to a better characterization of the device, which I know your customers will love, all without breaking a sweat.
Awesome. Okay, so what you saw there was that there were multiple test stations, and they were testing this amplifier. And we had a lot of data, tons and tons. If you saw the number up there, it was in the hundreds of thousands of data samples. And we were able to analyze all that data with AI and get you some insights that would have probably taken over a week to try to figure out. You know, with Excel or whatever, however you would do it, there's many different workflows. It's very hard. With AI, it makes it very simple, and it's all backed with a lot of math. So it's not like we're putting it in ChatGPT, you know, that can make up like 3 plus 3 is like 7 or 8. No, all that is done, you know, with a large amount of data with actual calculations. Okay, so you might be asking, okay, we're in a MongoDB conference. Where does MongoDB fit in all this? Well, oh yeah, all that data was in MongoDB. But let me show you some other, one very simple example of how you can put MongoDB, how we use MongoDB for AI. And so we have here the example finder for Nigel. The example finder allows you to talk to the AI and get some examples for those VIs that you can use in building new VIs. And VI is really a test program. Okay, it's just like a piece of code, graphical code. And so you can see here, find examples to show how to read and write from to a spreadsheet file. And it gives you some examples here. And then this one over here gives you a different prompt about acquiring data from one thermocouple, which is basically a thermometer. And then it gives you a little bit of blurb and then gives you some examples that it's found and describes those examples. So how does this work? So hopefully you have a little bit about the APIs for GPT, but if not, this is going to look like a conversation you might have in ChatGPT. Okay, so the ChatGPT and the APIs are very similar. So we're going to get a little technical here. So you have the system prompt. This is all super simplified, by the way. You help users with LabVIEW. Our actual system prompt is like pages and pages and pages and pages, but you help users with LabVIEW. And then we're going to teach it about this tool, find VI example, and it has a parameter for the prompt. What are we going to try to find? So say like you have had a long conversation about acquiring data with Nigel, and eventually you're like, hey, how do I save that to a CSV? And so the Nigel might say, sure, let's find you some examples that can help you with that. And then it's going to reply with a tool call. So this is an OpenAI thing. The other LLMs also have this, but an idea that the AI can reply with a function call and give you some parameters. Hey, I need to perform this action. Please go do this and tell me how it went. Okay, so find VI example, save waveform to CSV. See, it's a different text than what the conversation has been, because the AI knows how to create a prompt. And we've prompt engineered it how to use those, how to write it. And so then this is going to go and actually call in our orchestration, our agent framework, the actual function that then does a vector search into the examples collection. So we have a collection with all our examples inside of it, and then we vector search using MongoDB. And then we return those results as a series of documents, and then the AI can then reply. And the way that this looks like to a user is something like this. So when we're doing the tool call, we just give you a progress bar or give you some indication, notification that something is happening. So let's go back and take a look at this. and compare it to how traditional RAG is done. In traditional RAG, what we do is and there's many ways of doing this, it's just one, is you have an additional system prompt right after the last user's reply or message, and we include a whole bunch of documents that we've searched that somehow heuristically we found based on some prompt and some embedding. And so let's compare these two approaches. So on the left-hand side, we have tools, which we were talking about, and then RAG, traditional RAG on the right. So tools, you need an LLM that is fine-tuned for having tools. And so GPT models have those tool capabilities. RAG, any LLM will work. So anything you have, all the Llama models, it's all going to work really well with RAG. On the tools side, you can perform optimized and structured retrieval. Because you're calling a function, you can have different parameters on it. Hey, find me examples in this specific folder with this prompt. Those are 2 arguments. You can call any function with actual, real structured data. In RAG, you just have to do this yourself. You're on your own. You have to come up with some heuristic, maybe call out to a secondary LLM, and try to figure out how to retrieve the documents. It's very difficult. Tools, you have 2 trips to the LLM because you get the tool call and then you have to return a result and then you have to run it again. So it can get expensive, but only when the AI needs the information and the AI has formatted the right information for you to do the proper retrieval. In RAG, you do 1 trip to the LLM, but not really, because in every message you don't really know if you need to get documents, so you're going to go get them. Unless you have some heuristic to figure out when to go get documents, how many documents, does the user need documents at this moment, does the AI need those documents? It's actually kind of difficult and tricky to optimize this. And so you're kind of on your own to do that. And there's lots of frameworks that help you with this, but what we found is that the functions and tool calls do an excellent job, and it actually ends up to be much cheaper and faster in the end. And so how do you pick a vector store? So we talked about, let's compare MongoDB with some specialized ones, because we also use things like Chroma. We looked into things like Pinecone. There's many other vector DBs out there, but in a lot of the things that we have done, we have used MongoDB. So let's talk a little bit about that. So specialized vector DBs require you to operate something new. In MongoDB, we're in a MongoDB conference. Ideally, you already know it. You already have tools. You already have expertise around it. You know how to operate it. You know how to scale it. And so there's a lot of wins there versus something like Chroma, which is open source and local to yourself, and you have to figure out how to do that yourself. Specialized requires pipelines to move data to and from the vector store. So you need some sort of ETL process to get your data from presumably Mongo and go put it in something else. And so that's hard. That's a lot of complexity. But in MongoDB, embeddings are just columns in the existing documents. Couldn't get any easier. It's just another column in the existing document. You can go create another collection, fill it with other embeddings in it. You're using the same tools, the same knowledge, and everything. The key insight that we have here is that a vector store is just one small part of your AI solution. And all the math for all the vector DBs are all the same. They all give you the same things, mostly. There's some re-ranking algorithms that I wish Mongo had, but the base capabilities are all the same. It's just some math to go find the closest vector in your data set. So why not just use what you already know? And so what we have found is that an anatomy of an AI feature is much like an iceberg. All the cool, fun AI stuff is at the very top. It's like, oh yeah, we get to learn prompt engineering. We get to use a vector DB. We get to use an LLM. But a real AI feature has lots of normal, hard software engineering work underneath. You still actually have to pipe data to and from. You still have to manage databases. You still have to scale it. You still have user experience. You still have to figure out what you want to build. You have to put the button there. The chat is also a lot of UI you have to build. There's lots and lots of work in building an AI feature. And you have so much other things you have to do. So why not just use what you already have? It's just easier. And then maybe specialize it later if you actually have proven yourself that you have a performance issue or that you need a different algorithm that you actually is going to make a difference because you have telemetry and because you've talked to users, because your user is actually using it. And so that just gets to this obligatory XKCD about pre-optimization. This guy is optimizing his machine or his video for 4,000 CPUs, up from the old limit of 1,000. Like, who You can't even buy a PC with that many CPUs. And the basic thing is like, do you have support for smooth full screen flash video yet? No, but who uses it? The thing is, we're pre-optimizing. So MongoDB has the capabilities you need to at least get started, and then try to figure out if you need to scale beyond that. I don't know. I don't think you do, because there's many other things to try to tackle in a vector DB. And so nobody really knows exactly how AI is going to change our products and workflows. ChatGPT is only 1.5 years old. 1.5 years old. It hasn't been that long. And yet the entire world has changed because of it. We still have a lot of work to do. We're early, collectively, society, technology is early in this life cycle of trying to figure out how this technology works and how we're actually going to use it day by day. So your goal today should be rapid experimentation, using things you already know and then trying to figure out, get user feedback and be agile with it. And then optimize later, as makes sense. So right now what we're doing is building platform APIs. So what we call platform is these APIs that all our product teams use for knowledge bases that we're building on MongoDB that create documents, libraries of documents that we can build at runtime or dynamically or statically, that can support document-oriented intelligence, such as RAG, such as the tool call that we just saw, or structured extraction, which is a way to retrieve information from a document library. And then also this idea of a digital thread, which is basically like a news feed of everything you've done, and can we track in the conversation, figure out how to best help you based on what you've done in the past with the product. And so we want to support years-long, project-wide intelligence with this notion of a digital thread. And so in summary, MongoDB keeps our data. It gives us a vector store that we can search across it. It works today. And hopefully, and soon, it's going to let us do this on-prem, because a lot of our customers never want their data to leave their site. But it's worked pretty well, and we're pretty happy with it. And so that's what I have to say to you today. So I'll take some questions. Yes, we're here.
How many telemetry devices are connected to your AI model?
Telemetry devices.
For example, your test station. You mentioned you have 4 test stations, but what kinds of devices, other than just simple test stations, are connected, or is it just like test stations?
So trying to figure out. So basically, what we want to build is have modules, so hardware modules that are enhanced, that can do data acquisition enhanced with AI. So trying to figure out when to start an acquisition, if you have a trigger, like a 12-volt trigger. It's like whenever this line goes up to 12 volts, start an acquisition. But sometimes those triggers are not so simple. Like, oh yeah, you have a signal that just goes up to 12 volts. Maybe it's a pattern that you have to see. And when you see that pattern, maybe it's an Ethernet magic packet, then start the acquisition. And so those patterns and the different things that you would want to do, that can be enhanced with AI, because we can figure out when that is. You can give it a set of patterns. Hey, if you see something like this, then start the acquisition. So what we want to do is have AI in all our hardware, in all our software, and then have the ability for the AI to help the enterprise come up with intelligence. This is the idea of intelligent test. Sure.
How many teams and engineers in general were involved in the creation of Nigel?
I'm not sure I can share that information, but there's a lot of us. Yeah.
Awesome. I think that's time.
Cool. Awesome. Well, thank you very much, and I'll be up here if you have any questions you want to talk one-on-one.
Awesome.